Okay, so section 6.5 talks about what are called least squares problems. Least squares problems. Okay, what are those? All right, well, we'll get to that. But what we want to do is we want to have a geometric understanding of what it means for a system of solutions, okay, like A, X equals B, to have a solution. So what I'm giving you, these notes are helpful notes for section 6.5. And I would, and it actually relates to example 1, but I'm adding some detail into the notes and to help you get a geometric understanding of what's going on here with these least squares problems. So let me give you a moment to copy this example down. Okay, so we have a matrix A and a vector B, and we want to know, does this system have a solution? Does this system have a solution? Okay, so let's go ahead and see if we can get a solution to this system. So here we are on the next page. Here we are on the next page. And of course, the matrix equation, okay, this matrix equation then yields a system of equations that we wish to solve. Now, notice we have three equations. Hold on here, let me just get this set right. Yeah, we have three equations with two unknown variables. Three equations with two unknown variables. And okay, we want to solve that. Now, just because we have more equations than variables doesn't mean that we're going to have necessarily an inconsistent system. Two of the equations could be, for instance, the same equation, basically, right? So let's endeavor to solve this. Now, what did you learn? What have you learned how to do? Time and time again, you take this system of equations, you write the system of equations as an augmented matrix. And then you're going to do some row operations. You're going to try to get the matrix in reduced echelon form, okay? Or echelon form, but so what we'll do here is I want to get a 1 where the 4 is. So I'll multiply the first row by a fourth and replace the first row by a fourth times row 1. And then I'll have a 1 as a pivot here. And I'm going to take -1 times the first row, the first equation, and add it to the third row or the third equation, and replace the third row or third equation by that result. Okay, so very basic stuff here. And then where the 2 is, I want to get a 1 as a pivot. So I'll multiply the second row by a half and replace the second row with that result. Are there any questions so far? Okay, good deal, very good. And remember, we have an augmented matrix here. Augmented matrix. Okay, so what I want to do now is produce a 0 where this 1 is. So I'm going to use the second row, multiply it by -1, and add it to the third row. Right? So when we do that, okay, and please let me know if I'm going too fast or if you have any questions. Okay, when we do that, we end up getting this augmented matrix. And hold on here. One moment. Let me put in that last step there, -1 times row 2 plus row 3. Put the result in row 3. That's what we did. And the last equation, okay, here, if we read it off, it says 0x1 plus 0x2 equals 21/2. That has no solution. So our system is inconsistent. It has no exact solution. And you've encountered this before. You've had systems of equations where there is no solution. But what we want to do here, what will be very helpful for understanding section 6.5 is to interpret this process geometrically. Okay, we want to interpret it geometrically. Okay, give you a moment to catch up here. Okay, so in this problem, what we had was a matrix equation. So represented by A times X equals B. And we can write the matrix equation as a vector equation. You learn that a matrix equation can be written as a vector equation. And then a vector equation is a system of equations. Now the vector, if we think about that matrix A had columns 4, 0, 1 and 0, 2, 1. So it was a 3x2 matrix indeed. And the first column vector of the matrix A we'll call a vector A1. The second column of the matrix A, we'll call that vector A2. And that is indeed the vector equation we're trying to solve here is, can we find some x1, some multiple of vector 1, plus x2, some multiple of vector 2, and the linear combination. I mean, what this means is here, this vector equation, is there a linear combination of the column vectors A1 and A2 that equals the vector B? Now, we know the answer is no to that, but this is what we're trying to do. So the question is, how can we understand this process here in a geometric manner? How can we understand this in a geometric manner? And I'll just make a note here too. Note that the vectors A1 and A2, they're not orthogonal to each other. Okay, they are not. These vectors are. I mean, it's not necessarily relevant here for what I'm trying to talk about, but they're not orthogonal. All right, so let's go ahead and try to figure out geometrically what it means when we're trying to solve a matrix equation or system of equations. What is, like this, what does it mean geometrically? Well, the matrix equation gives us this vector equation. What does that mean geometrically? Mikhail's saying draw the vectors. That's exactly right, Mikhail. We're going to actually do what you said. Mikhail says draw the three vectors, A1, A2, and vector B, in three-dimensional space. And look at what happens. And he's right. So that's what we're going to do. That's what we're going to do. So remember, what we're looking for here is we're looking for scalars x1 and x2 such that this vector equation, or equivalently the matrix equation, is true. But we know it's not. We know there is no scalars. There is no solution x1 and x2 that will work. But what does that mean geometrically? Well, here's what you can do. Define W to be the span, the subspace that consists of the span of vectors A1, the column vectors A1 and A2. So the column vectors A1 and A2 of matrix A, let W be the span of those two column vectors. That's a subspace. Any span of any set of vectors is automatically a subspace, right? The dimension of that subspace W is 2 because the vectors A1 and A2 are linearly independent. Clearly, they're linearly independent. Now, since x1 and x2 don't exist because there's no solution to the system of equations, geometrically, we have the situation that you see here in this picture below. So the span of the column vectors of the matrix A, this span here, that's by definition the column space of A, right? And so you have in the picture, a column, a subspace, column space of A, and naturally the column vectors of that matrix A are in the subspace, but the vector B lies outside the subspace because the vector B is not any linear combination. It's not any linear combination of the column vectors A1 and A2. So the vector B cannot be in the subspace. It can't be in there. It has to fall outside. This is geometrically what it means when we say that a matrix equation does not have a solution, or a system of equations does not have a solution. This is the geometric interpretation of it. So we've geometrically verified our answer here with this picture, and it makes sense based on. I mean, if you can just tell looking at vectors A1, A2, and vector B, you can just well, vector B is clearly outside the column space of the matrix A. Please let me know if you have any questions about this. Please let me know if you have any questions. All right, who's feeling reasonably good so far? All right, very good, Cameron. Very good, Mikhail, excellent. Okay, well, good, Marcella, very good. Okay, so sometimes a system of equations just does not have a solution. Very good, Jacob, wonderful. Sometimes a system of equations just does not have a solution. But perhaps we can find another kind of solution. Okay, and we call that solution a least squares solution. Now, what is a least squares solution? Well, let's look at this example again. Okay, we're going to look at this example again. The same matrix A, same vector B, and we agree that the system does not have a solution X. But it does have what's called a least squares solution, which we denote by the vector X with a hat over it. Okay, with a hat over it. So we're going to find the least squares solution for this system. And then we're going to determine what's called the least squares error for our least squares solution. So let me give you a moment to copy that down. And let's remember what we're trying to do. Again, when we look for a solution, okay, vector x is x1 and x2, and what we're looking for is x1 times 401. Hold on. Let me rephrase this. Hold on. So when we solve a system, when we try to solve a system, what we're trying to find is values x1 and x2 such that x1 times 401 plus x2 times 021 equals 2011. But we know that that's not going to ever happen. There is no, we just showed it. There's no x1 and x2 such that a linear combination of the vectors a1 and a2 equals the vector b. But what we could try to do is find some linear combination of the column vectors of the matrix A, A1 and A2. Find some linear combination of A1 and A2 that gets us as close as possible to the vector B. I mean, in other words, the left side here will never equal the right side. But maybe surely there must be values of x1 and x2 that would make the left side as close as possible to the right side. And Mikhail, a projection is involved. So let me show you graphically what we want. Here's our situation. Here's the situation we have. Okay, we have our vectors A1 and A2 that are part of the column space of the matrix A, because those are the column vectors of the matrix A. And then that vector B, okay, that vector B is outside the column space. Well, the best we can do is find a vector in the column space, okay, who's closest to the vector B. Well, that is going to have to be the projection. That is going to have to be the projection of the vector B onto the column space of the matrix A. That's the best we're going to do. If we can't solve the system exactly, let's try to get some solution that will I want to say it right. We want to get a solution. We want to get choices. We want to get values for x1 and x2 such that I want to say this the right way. Such that we can get close as possible to vector B. In other words, well, let me give you a moment to copy the picture down. Let me give you a moment to copy the picture down. One moment. Please let me know if you have any questions. So are we in agreement that this projection vector, denoted by B hat, is the closest vector in subspace W to the vector B? Are we in agreement with that? Is there any other point? Is there any other point in the column space of the matrix A whose distance is as close to the vector B as is the projection vector? I think you'd agree that there's no other vector, right? No other point. So what we want to do is find this projection vector. And there is a solution, x hat. And this is, by the way, what's called a least squares solution. Mikhail, x without the hat is an actual true solution to the system of equations, but that doesn't exist for our situation. But the least squares solution would be the linear, it would be the values x1 hat, x2 hat, such that ax hat equals the projection vector. Well, you see, Mikhail, there is no existing solution to the system of equations. So the best we can do is find the least squares solution. That's the best we can do. It's B hat always exists. That's correct. B hat always exists. We can always find the projection of a vector onto a subspace. That's correct. Well, I'll tell you what, let me show you. All right, well, okay. Let me, I think if I go into the book a little bit, it will be helpful. But just keep in mind that whenever, like if you look at the picture here, okay, if you look at the picture, okay, so like this could be a times x1. Maybe that gives you a point over here. Okay. This point down here could be well, this point here could be a times the vector x2. Only a times the x hat vector, which is the projection of the vector b onto the column space of A, only that vector will be the closest vector to the vector b. You see, we can't solve ax equals b. Their ax for any vector x, a times x will never equal the vector b. So the closest we can say is, well, let's try to find a least squares solution so that the error, okay, so that this error here, this error, hold on, one moment, so that this error is minimized. We want this error, which is b minus, well, we want this error, I'll just, this here, we want that distance to be minimized. Okay, so like when you want to find the distance between a point and a plane, you find the length of that vector there. We want that distance to be minimized, and the least squares solution will do that. And so, of all the vectors, a times x, it is the vector a times x hat that minimizes the distance, the difference between the vector b and a times x hat will always be less than the vector b and a times x for any other x. That's called the least squares solution, because when you take the length of a vector, if you take the length of a vector, like if you, let's just say you had some vector, some vector a, the length of that vector is the square root, let's say it's a 2×1 vector, it's the square root of the sum of the squares of the components. That's why we call least squares. Let's see, Mikhail says, yes, a times x hat is the closest vector to the vector b compared to any other vector x. That's correct. That's exactly right. And what we want to do now is we want to find that least squares solution. So one moment, let me bring up the book, the ebook. Yes, the vector x is arbitrary. Yes, yes. Okay, let me bring up. So we're not done with this problem yet. But now what we have to do is we have to figure out a way to compute this vector x hat. We have to compute those the least squares solution values. You're welcome. You're welcome. So how are we going to do this? How are we going to do this? Well, let me go to the book here, and we'll come back to this. So, you know, the book states the same thing that I stated regarding the least squares solution. And pictorially, I like the pictures in the book too. See, figure 1, the vector b is closest to the vector a times x hat than to a times x for any other vector x. And a times x hat, it turns out, would have to be, okay, so I'm looking here at figure 1. A times x hat would have to be the projection of the vector b onto the column space of A. Okay, so now we go to figure 2, and b hat is a times x hat. B hat is the projection of the vector b onto the column space of A. But now we have to find that. So how are we going to do this? We can't use the orthogonal decomposition theorem to find that projection vector b hat because we don't have an orthogonal basis. Okay, we can't use those nice formulas that we saw in section 6.3, theorem 8, the orthogonal decomposition theorem. We can't figure out what x1 and x1 hat and x2 hat are. But geometrically, we know that if, okay, we know, let me just make this, we're fine here. We know that if x hat satisfies ax hat equals b hat, in other words, x hat is the least squares solution, then the vector b minus b hat would be orthogonal to the column space of A, and so b minus a times x hat is equal to b hat. That would be orthogonal to any column vector of A, of the matrix A. So basically, what this means is that if you were to take the dot product of any column vector A sub j with that vector b minus a times x hat, you see it there in figure 2 in the picture, the dot product would equal 0. And another way to express a dot product is to take the transpose of the matrix of the vector A sub j, that column vector, and multiply it by the vector b minus ax hat. Okay, that will equal the scalar 0. Okay, that will equal the scalar 0. So let me just show you something here on the whiteboard. So one moment here. So if you have the dot product here, between these two vectors, dot product, and the vectors, let's say, hold on here. Yeah, this is an n by 1 vector. B minus a, B minus a x hat is an n by 1 vector, and the vector aj is an n by 1 vector. Well, you can, and let's say that equals 0. You can express a sub j as aj's transpose and multiply it by the vector b minus ax hat, and that'll equal 0. Because b minus ax sub hat, again, that has n rows by 1 column, it's a vector, but a sub j transpose, well, if a is n by 1, a sub j transpose is 1 by n. And you can do this for all the column vectors in the column space of A, for all the column vectors. Now, let me just be very careful here. I want to make sure that my that I got everything written correctly. One moment here. Actually, I do have one mistake here. In the book, hold on here, everybody, one moment. Yeah, the vector B and A times X hat are in m-dimensional space. So the vector B minus AX hat is m by 1, and the vector A sub j is, it's an m by 1 vector, okay? So we are taking then when we write AJ transpose, that's a 1 by m vector, we're multiplying it by m by 1 vector, that equals 0. And that's true for all the column vectors of the matrix A. And what you can do is this statement here, you can incorporate all of this into a matrix equation like this, where B minus AX hat, that's m by 1, the matrix A is treated as an m by n matrix. So A transpose would be n by m. And so the vector 0 is an n by 1. Okay, so you end up getting an equation here that we can solve, that you can solve to figure out what the least squares solution x hat is, right? Because that's what you're looking for. Now I'll go back to the book. I'll continue this back in the book, But are there any questions so far? Okay, very good, very good. Cameron's good, wonderful. All right, so let me go back to the book here. You need the transpose because you have to incorporate all the dot product information. The dot product, let me just, the dot product of any column vector, hold on. The dot product of any column vector of the matrix A with the vector B minus A x hat would equal 0. And that means then that we write that as the transpose. We can write that as a, as just a matrix multiplication between vectors AJ transpose and B minus AX hat. And if we incorporate that for all of those column vectors AJ, if we incorporate all that information, we end up getting this equation here, and we can solve that. See, we can solve that for the vector x hat. So what they do is they distribute A transpose. Okay, they distribute it across there. Okay, no problem, Mikhail. And this is why I'm going carefully through this. And then A transpose times A times x hat would equal A transpose times B. Hold on, did I miss? Hold on, yeah, okay. And so you end up getting an equation that you can solve. And the equations that result, okay, from this A transpose times A times a vector x equals A transpose times a vector B, that is a system of equations, and those are called your normal equations. And for some reason, they drop the x hat in equation 3. You see that, how they just sort of like leave the x hat off? I think it should be in there because that's what it means. And they even say that a solution of the third equation is often denoted by x hat. So by theorem 13, the set of least squares solutions coincides with the solution to those normal equations. And that's how we're going to find our least squares solution. That's how we're going to find it. So what we're looking for in our example, we're looking for the least squares solution of the system A times X equals B, where our matrix A consists of column vectors 4, 0, 1 and 0, 2, 1, and the vector B is 2, 0, 11. And now we're gonna utilize these normal equations to find the least squares solution. Okay, and so let me take you through that process here. Okay, so back to our, here we are. We want the least squares solution. So here we are. So from the textbook, okay, we learn that we find the least squares solution by solving the normal equations. And in this case, our matrix A, I put in below all the dimensions of every matrix, every vector, so you could see that it works out. And now we have to set up these, so we're trying to solve for the vector x, that 2x1 vector, but we need to figure out what A transpose A is, and we need to figure out what A transpose B is. And that I do below here. Now I want to mention, you'll notice that A transpose A here is a square matrix. It's a 2x2. So for this system of equations here, since A transpose A is a 2x2 matrix, it's a square matrix. And whenever we think of a square matrix, we can consider, well, is there possibly an inverse? If there were, then x hat would equal A transpose A inverse times A transpose B. That's assuming that the 2x2 matrix, right, A transpose A, that's assuming the 2x2 matrix is invertible. Well, it is going to be invertible because the columns of the matrix A, here's A, the columns of the matrix A are linearly independent. So if the columns of the matrix A are linearly independent, then A transpose A has an inverse. And the proof of that is not hard. Actually, you'll see that in one of your homework problems in the multiple choice. So we can figure out that we can get A transpose A, and I did it using the inverse formula for 2x2, but you could do inverse of A in MATLAB and get this inverse. That's fine. We want to use MATLAB to help us here. Now, what would happen if A transpose A is not invertible? Well, we'll look at that. We'll look at that after the break. We'll look at an example like that. But now that we have A transpose A, we're ready to find the least squares solution x hat. Are there any questions before I move to the next page? Give me a thumbs up if you're feeling good so far. I'd like to make sure everybody's comfortable. Jacob's good, Bellin's good, wonderful. Mikhail's good. Marcella's good, excellent. Okay. So here we go. So we have now, again, this was our system of normal equations, and I already told you that since A transpose A is invertible, the least squares solution x hat can be found using this equation. But I was just over here, this previous step, I just wanted to, show you how we got here. And now we just work it out, and we end up getting 1, 2. That's the least squares solution. Please let me know if you have any questions. Okay, well now we know what x hat is. We know what our least squares solution is. Now what we want to do is determine the least squares error for this least squares solution. That's the next thing we have to do. Okay, so what we do then is, okay, well, yeah, what we do is the projection vector b hat is equal to a times x hat. And that will be 4, 4, 3. And the difference between the vector and ax hat, okay, this here, so Mikhail, I believe you were saying this here, this is the z that you see in the pictures, right? That's that vector that projects down into from the vector outside of the subspace to the subspace. That's right. It's the orthogonal. It's not the orthogonal projection, but it's the distance between the vector b and the orthogonal projection. That distance is going to equal -2, -4a. And so the least squares error, this here, is your least squares error. So if we can't solve a system a times x equals b, let's try to find, if this does not have a solution, what we can do is try to find a least squares solution ax hat so that ax hat approximately equals the vector b. That's what we're doing here. And the best approximation would be the approximation that makes the difference between the vector b and ax hat as small as possible, right? As small as possible. And that's called your least squares solution, x hat. And then that gives you your least squares error. You'll see in section 6.6 that, like linear regression, the line of best fit through a set of points, can be thought of as I'm explaining here. There are many practical applications to this, which you'll see in section 6.5. We'll cover that on Wednesday. But are there any questions? Any questions at all? Mikhail's good. Cameron's good. So I appreciate it. Generally, when I pause, of course, if there are no questions, feel free to say a thumbs up, okay? Because give me a thumbs up if you're comfortable. Cameron's comfortable. Mikhail's comfortable. I'm trying to make sure everybody's comfortable here with what we're doing. Marcella's comfortable. Wonderful. And Belen, good. And Jacob. Yasin, how about you? Are you comfortable? Or Fatima? Or David? Or Zishan? How about you all? Fatima's good. Okay. Wonderful. Okay, so sorry about that. My computer had to restart or something. I don't know. Well, hold on. Get out of here, Adobe Flash. I love you, Adobe Flash Player, but I don't want you now. Okay, you ever have things that kind of pop up? They pop up like out of the blue, you know? Update time. Okay, that must be what's going on, Cameron. Well, all right. Well, look, hold on. Now, Zishan or Yasin, somebody had a question here. Oh, Flash. So Cameron, maybe. Well, I don't know what was popping up there, but at any rate, who had a comment here? Okay, was it Yasin or I see Cameron and Mikhail have some comments here, but somebody had a comment. I don't want to leave anybody out, but I think you're good. Okay, let me go ahead and stop the recording here. Excellent. This is in our recording. Very good.